right. So first, thanks a lot for the invitation. I was really sorry last year to not make it. I was looking forward. I've been hearing about KCD Denmark for quite a while, so I'm very excited to be here. Yeah, so like as an introduction, I lead a couple of teams for platforms at CERN. We focus mostly on cloud-native deployments and machine learning platforms. And I also do quite a bit on the Cloud Native Foundation. I participate in the Technical Oversight Committee and what's called the End User Technical Advisory Board. It's mostly about checking that accepting projects into the foundation, checking their maturity levels and things like this, and helping end users like I'm sure a lot of you follow this. Yeah, so that's me. What I will talk about today is a bit to the journey that we had, and me personally as well, but at CERN about using Kubernetes. We actually started using Kubernetes quite a while ago. Anyone knows what this is? These pictures are from? Yeah, so this was KubeCon Copenhagen in 2018, which was actually in this building. I had been in KubeCon Berlin before, which was much smaller. This was the first pretty large one in Europe. And you can see, actually, we submitted a talk, and we got it accepted. And this is what got us into the community as well, being part of CERN. Actually, that's me on stage with Klenimar. Klenimar came to CERN to do a summer internship for 3 months, was playing with Federation, and this was his first talk on the keynote stage in front of 4,000 people. It was the first talk in his life. So he was pretty overwhelmed about the reception. But you can see the chairs. It was Kelsey and Liz at the time. You can see probably some familiar faces here. There's Cheryl. There's some known people there in the middle. Lukasz here. There was a great talk. If you want to see the video, there was a great talk from Simon Warley. And he was basically taking war metaphors to explain how Cloud Native was about going after AWS, which was a really entertaining talk. So if you want to check it, I would suggest. But it was a pretty big event. So this was kind of where we were at the time. We weren't sure Kubernetes was going to be the thing. We had a good feeling. But there was Docker Swarm, there was Mesos. Actually, Docker had DockerCon here as well. Which was basically about Swarm is taking over the world. And that seemed like a reasonable thing. Then everyone's saying Kubernetes won't scale. You need dual level scheduling. You need Mesos. Twitter uses Mesos. So, okay, maybe Mesos is the thing. But then slowly we went to, okay, Kubernetes, we use it for this. Then we use it for a lot more. And basically, eventually, it took over. But during this journey, we kept being asked questions. Questions like, you can't do scale with Kubernetes, and this was actually a thing. So we started trying it out, and Google was publishing some regular reports. And Brendan Burns, that was at the time at Google, is now at Microsoft. He had a blog post where he said 1 million requests per second, and then he was showing how they could do this in Kubernetes. And he had this really nice demo. And we decided, okay, we want to do like Google. So we went for it, and we started evaluating what we could do with Kubernetes, and you can see there are like clusters of different sizes, and we eventually got to clusters of 1,000 nodes. And you can see the time it took to create them. It's kind of flat until 128, which is what we expect, and then it was started to be linear, but still like 1,000 nodes in 20 minutes back in 2016, it wasn't the worst thing in the world. And then we started trying the actual scale. So Google did 1 million, and we did 1 million, and then we tried 2 million, of course, because we wanted to beat Google. And we managed. And then we tried 10 million, because Google did 10 million after. So we did manage this. As I mentioned here, like the scaling was pretty good for 1,000 nodes. But then when we tried 10 million, we started thinking, OK, it's not really about scaling Kubernetes. It's about scaling our own infrastructure. Because when we started scaling to 10 million, we reached 7 million, and we were debating in an office what's going on, everything is slow and whatever, and then there was a lot of excitement in the building, and I went back to my office, and I had a lot of missed calls from the network team, and apparently we had fried a switch that started broadcasting all the traffic across all the data center and basically brought the whole thing down, and we were told to very gently stop the exercise, which we did, which is fair enough. And then we went scaling bigger. So we wanted a shiny thing. So we submitted a talk also for KubeCon Barcelona, where we tried to do the rediscovery of the Higgs. It was kind of a stunt, but it was like taking the analysis that gave the Higgs discovery back in 2012 and the Nobel Prize in 13, and try to redo it many years later with new technologies, but actually the old software. And this was to show that first we could reproduce things that were legacy in newer infrastructures, and we can scale out to the to the public cloud. And in this case, we used the Google Cloud, and we could process 70 terabytes with a cluster of 25,000 cores. And we actually did this on stage, and it took less than 5 minutes, and you could see this is the plot that showed the Higgs discovery. You can see the data actually being discovered live on stage. That was pretty exciting, very visual, and it showed, yeah, we can scale pretty well with Kubernetes. So that thing, gone. And now, like just last week, Google announced clusters of 65,000 nodes, and apparently people actually run this, so yeah. So then that was solved, we can scale. And then people started doing, yeah, but it's only for containers. You can do containers, but you can do only containers. So we took the challenge. So I'll do a few live demos. I have to say that I didn't bring I forgot my live demo lucky sweater. So let's see how this goes. But I do have a few live demos to show you. So the first one I'll show you is, yeah, sorry, I forgot to show something. You can only do containers. You probably heard of projects like this too. Like KubeVirt focuses on virtual machines. Crossplane focuses on extending Kubernetes to a lot of things. So you'll find providers like for OpenStack, GCP, AWS, wherever, all the providers, and a lot of other things. So people start doing really funny things with Kubernetes. So the first demo I'll show you, I hope this is big enough. So in this case, we basically are using Crossplane. And at CERN, we also have an OpenStack cloud that manages virtual machines, volumes, things like this. So we started looking at, can we actually control some of these things using Kubernetes so that we can do declarative YAML and reconciliation for this kind of thing, which is quite a big step if you're used to doing like Terraform or Ansible or Puppet. It's a big step to start having reconciliation. So in this case, you can see that here I have a virtual machine running. And I'm getting it using Kubernetes, and this virtual machine is actually running on our OpenStack cloud. It's available right now. And you can see how this is defined. So there's a CRD from Crossplane. I give it a name. I give it a flavor ID, an image ID, the key pair, and some metadata, the network I want to use, all of this. And this is how it works, so it's pretty easy. If I do create a new one, we should see it appearing here. So it says it's synced and it's being created. So if I actually list, so this is running on our cloud at CERN, so bear with me if this fails. But we should see here the results. So you see that I had this KCD VM active already, and this one just got created and it's being built. So you see here the state. While it's being built, what I'll do is I'll show you what you can actually do. So this is how you can extend Kubernetes. It's pretty impressive. Like I install Crossplane in a provider, and suddenly I can do declarative YAML for all these things that we've had for ages. And this is a big thing, because then you can integrate with Argo. You can do all the usual things we are used to in cloud native for things that were quite complicated to maintain before. So you can see, like, I don't know, database as a service. You can manage flavors. You can do floating IPs. You can do instances, which is what I'm doing now. Create volumes. There's a ton of things that suddenly become available. And actually, you see the VM is available now. So if I do a describe on this machine, I will see here all the metadata. And if you're used to the OpenStack CLI, just the fact that this is so fast is already worth all the trouble. You can see here the IP. So in principle, if I ping it, there you go. So I created a VM using Kubernetes, no knowledge of anything else, and suddenly I can do declarative YAML for all of this. And you can do some similar things for key pairs and all sorts of things. So this is a big improvement. I have 3 more demos, so maybe. So at least one out of 4. So the next question is like, okay, can do all this fancy stuff, but you can't do critical. Like you can do your things, batch, whatever, but don't put my critical things on Kubernetes, please. And I'm sure everyone is using things that are critical for your own organizations, but like, let's look at critical things. Like, there was an amazing presentation at the previous KubeCon from Huawei where they showed how they are doing satellite imagery, and they actually onboarding the satellite software. They're basically running the kubelet or a version of the kubelet from KubeEdge on the satellites, contacting a control plane here on Earth, and then monitoring their satellites for the status, and they are doing image recognition. And it's pretty cool. They use the data centers on Earth to train their algorithms and the models, and then they push them live to the satellites, and then they start doing image analysis and bringing the data back to Earth. And you can see the architecture there. So this project is pretty cool. KubeEdge, that's just got graduated as well in the CNCF. So it's pretty, if you have Edge, I was just talking during the break before about excavators, which for me somehow become Edge devices now. So if you have ideas on how to do things like this, this is a pretty cool example. There's another one which is amazing. There was a talk by Nicholas a couple of years ago. He used to be the CSO for the Air Force in the US. And they had an amazing exercise, which is let's put Kubernetes on F-16s. And they actually did it. And you can see the video online. It's pretty amazing. Like what they start describing is things like they put the restrictions they have to actually deploy this. And it's we need to be able to reboot all the systems inside the jet in under 2 minutes. And it's like running the stuff that I'm running in my laptop. So I found this like a pretty amazing critical deployment. And then here you have a U2, which also runs image recognition algorithms. And again, here it's not controlling the systems inside the plane, but it's controlling the systems that are actually doing the image scanning from these flights. So that's pretty cool as well. And then one that is closer to what I do, which is particle physics. So we've been working on what we call high luminosity upgrade for the LHC, for our detectors. And this will increase the amount of data we collect by 10 times. So these days we collect something like 100 petabytes a year, and we'll be collecting 1 exabyte a year very soon, in a couple of years. So if you think about this detector, it's 100 meters in the ground. We're doing proto-proton collisions and generating 40 million collisions a second, generating more than 1 petabyte a second, and this has to be filtered to something that we can manage. And you can see here, this is from a presentation from a colleague of mine just last week. You can see here how it goes. You have these 40 million collisions, these 5 terabytes a second after the first hardware filtering, and then we have this event filtering farm, which is a big cluster underground of around 30,000 CPUs these days, and this will be fully on Kubernetes in a couple of years. It will be one gigantic cluster doing all the Atlas online filtering. And you can see here what they had to experiment with, which is to deploy almost 30,000 applications in less than 60 seconds. And they actually achieved, through a lot of optimizations and work with upstream Kubernetes, they actually achieved this. So that's also as critical as it gets. Like if we don't get this data in, it's basically burning electricity in this particle accelerator. So this is the critical things in the lab, and we are now using Kubernetes. So we've come a long way. So one that kept coming, okay, you can't do batch. Like batch schedulers are super complicated. You need Slurm, you need HDConder, you need all this complexity. Kubernetes was developed for services, so you can't do batch workloads. So this is not true anymore. Maybe some have heard of these projects like Volcano. Probably someone has tried. There's another one developed by a company called G Research. It's called Armada. And there's a new one that is called Q that started around 3 years ago. And it's basically trying to do all of these primitives inside Kubernetes itself. So I'll try another demo here, which is this one. So this is basically what Q is about, which is extending Kubernetes to support the advanced primitives that a batch system requires, which is queues, some sort of priority, co-scheduling or array jobs or gang scheduling or how you want to call it, and then quotas and all these things. So here I will give an example, which is we have one queue, which is called a cluster queue, and this is where the resources are actually exposed by the admin. And here you can see I say, for example, what kind of resources and how much I allow. In this case, just for the demo, I put 2 CPUs. I also say that I enable preemption, which means if I have jobs queued, some jobs with higher priority can preempt other jobs that are already running. And then I have a flavor, and I have the different priorities defined, one for high and one for low priority. And then after this, I have one job with low priority, so this job is doing nothing special, it's just sleeping here, but you see that its job is actually deploying one instance. And I have the exact same thing for a high priority job. So the only thing that changes is really this priority class here. So what we will try, is to create first one job with low priority, and you can see that it goes to suspended. This is running on a local cluster, a single cluster. And if I deploy a new one, so if I describe this job, you will see what it's doing. The scheduler is just admitting the job and then creating the pod, and that's it. Because there's capacity. Each job is taking 1 CPU, and the cluster queue is advertising 2 CPUs. Now, if I deploy another one, because I only have 2 CPUs, this job is now suspended. So it's waiting there. So basically, I can do batch scheduling in Kubernetes today. This is queue with upstream Kubernetes. There's nothing else. And I can already do everything I've been asking for. So just to show you that also preemption works, so what I will do now is I'll deploy a job with high priority. And you can see that here, this job will immediately be picked up. Not only that, it had to remove a lower priority job to make space for this new one. And if we check which one it was that it shows, it's this one, I think. Let's check here. So you see here that it tells you that the job was running, but suddenly it was preempted to accommodate another job that has higher priority. So it deleted the prod, put it back in suspended, and as the jobs will finish, and these jobs run for 2 minutes, then it will continue going. So basically, it's declarative YAML defining the queues, some priorities, and I have a batch system on Kubernetes. So that's pretty cool. So again, you can do batch, no longer the case. We can perfectly do batch. If you want, you can use tools like Volcano that are extremely popular in companies, especially in China, and they have crazy deployments with tens of thousands of nodes. Armada, which is from this financial institution, or just upstream Kubernetes with queue. So you can perfectly do batch these days. Now, the next one is everything works if your users are really well behaved. And I will give an example. There's many, but one example that comes very often is if your images have to be really well structured. And this is true for our case because when we do batch-like workloads, we deploy thousands or tens of thousands of jobs in one go. So if your images are not well behaved, you're basically taking a denial of service on your whole infrastructure because you have tens of thousands of units pulling whatever the size the image is in one go. And if these images are hundreds of megabytes or gigabytes, suddenly you're pulling from one registry and just blowing the network really fast. Now, one question I have, what would be a badly behaved user in terms of images? Like, how many of you have to handle images that are 100 megabytes? Raise your hand. Quite a few. 1 gigabyte? 10 gigabytes. One there. Okay, I'm sorry, but yeah. 50 gigabytes? No one. Okay, so I'll do another demo, which is this one. And in this case, I will show you okay, I'll introduce this first. So I'll show you a cool tool. We have images that are really ridiculously big. Somehow, I found one company that has even bigger ones. So we have been discussing with them also how to solve that problem. But basically, what someone at Google, that was working at Google at the time, discovered, pretty smart person, they discovered that something pretty basic, which is a tar of tars is still a tar. But if you make a tar of tars, you end up with a seekable tar. So they called it seekable tar GZ. And what they do is for every tar, because a Docker image basically is just tarballs, or an OCI artifact is the same with some metadata. So what they do is they take the image, all the files, and they tar every single image, and then make a tar out of all of that. And what you end up with is an addressable set of files, which means that you don't need to necessarily download a full image before you start workload anymore. You basically do a remote mount, and every time the workload asks for a file in the file system, you have some sort of fuse mount that will fetch that file individually by asking the registry for that exact address. And this works beautifully. So there were some changes needed in tools like Containerd and all the stack to support this kind of workload. But what we end up with is really like, instead of pulling the image and starting a workload, which can be pretty slow if the images are gigabytes and you have a lot of them, you just remote mount, and every time the workload asks for a file, you just download the exact files the workloads need. This is really important for things like batch, because people tend to blow their images with all the code they might need ever in their lives for their jobs, and then they only have to pull one image and everything works all the time, instead of structuring their images. And we try to go to them and explain, maybe do it better, but yeah, not everyone has the time to do it. So what I will do is I will show you a demo with amazing images. So this is one project we have, and it's quite spectacular. Huh? They push versions of this. This is for FPGAs, and every single version is hundreds. It's tens of gigabytes, 100 gigabytes in some cases. And it's not like they share layers. They just blow them and push. Everything is a new one. So it would end up pulling the whole thing every time. So what I will try to do, I have a cluster here that has a few nodes, and some nodes, the first two, are without this seekable tar GZ enabled, and the three lower ones are with seekable tar GZ. So I put some taints and tolerations. You can see that all the job is doing is trying to pull the image, which is what we want in this case. So I will apply this with no star-gz. And it will start pulling the image. And you can see here it's containing. One thing that I will say is that these nodes only have 20 gigabytes of disk space. So it's trying to pull a 90 or 100 gig image on a 20 gig file system. You can imagine what will happen. It's pretty easy to imagine what will happen here. And if we check what it's doing here, this pod. So here it's still thinking that it will actually manage. It's been 35 seconds, 40 seconds. Okay, you see an error now. So you see where this is going. If I describe it here, it's saying I failed to pull the image because there's no space left on device. So there's absolutely no way we can run this job in these nodes. But come back to star-gz. And in this case, the only thing I will do is exactly the same, but I put a toleration on this, this feature is called lazy pooling. Actually, Google introduced it in GKE as well. It's called image streaming. AWS has a similar tool for this kind of thing. And so in this case, I put a toleration for lazy pool, which means it goes to one of these other nodes, which actually is exactly the same node, just with this feature enabled. And you see that it's running after 6 seconds. And it's successfully pulled in 1.7 seconds, which is basically the time to do the fuse mount. That's nothing else that it's doing. Now, what happens is that actually when the job is running, or the workload is running, it's actually pulling the files as it goes. So it's a bit slower at the time. Then it caches the files locally. So it might be that there's a warm-up. So there's another version of this format that is called Enhanced Seekable Tar GZ, ES-tar-GZ, which basically, when you build the image, it runs the entry point that you define on the Docker image and records the files that are loaded by the entry point and puts them on a special area in the tarball so that you actually pull just those absolutely essential files that are in the entry point. And this kind of speeds up the process. It slows down a bit to start, but you gain a bit. But basically, this was something that we absolutely needed. And yeah, so now you can have 1 terabyte images. It doesn't really matter. It's just a remote mount anyway. So that's demo number 2, and 3, actually. Yeah, it's going good. All right. So then the last bit I wanted to mention is you can only do single cluster. And this was a thing, like Kubernetes was actually designed single cluster. If you have to deal with this, you will painfully understand that the design was single cluster. There's a one etcd. If you want to do multi-cluster, there's still one etcd, and you have to figure out something else. Now, if you're doing services, as per the service definition of talking service to service, there's actually quite a lot of options. There are options like Cilium, Istio, Linkerd that will do the service mesh, and service meshes actually can go multi-cluster quite easily. They have this notion of egress and ingress gateways. It can go really far with this kind of tool. But if you're doing batch, it's a bit more complicated. So there's 2 projects that are interesting. The one in the middle there is called Karmada, and this is actually a version of something we asked for in that keynote that I mentioned in Copenhagen, which is federated Kubernetes. There were many iterations of this kind of thing over the years. There's this project Karmada that does this kind of thing. But we actually also worked with the Q team to introduce on a feature that's called multi-queue. And multi-queue is really what it says. It's instead of having 1 cluster, like the demo I just did with cluster queues and local queues, you can have multi-queues where we have a central cluster that receives all the jobs, but actually has policies to deploy those jobs in remote clusters. And these clusters can be on-premises in the same data center next to the main one, but they can also be in the public cloud, or can be in HPC supercomputers. They can be pretty much anywhere. And that makes it quite powerful. So that's the last demo I'll do today. And I did, if you were at KubeCon last week, I did this demo there as well. So this is kind of a repeat, but I have a little bit more time here. So basically what I'm doing is I'm managing a couple of clusters using Argo. And you can see here the important part is this one, which is the master one that is receiving all the jobs. And then I have 2 worker clusters, one running at CERN in the same data center, and one running in a public cloud. And the definition of this is, again, just YAML. You can see the queue configuration, not really important. Well, what's important is this cluster queue. So this is a local queue, basically what I did just before. Not really interesting for this demo, but the interesting ones is that you have 2 queues. One is on premises, and one is external. And each of these queues, this is just how we define it in YAML, is having what we call worker sets. And this is basically the lists of clusters that can take jobs from these queues. So for the on-premises, it takes this worker set on-premises, and for the remote one, it takes a worker set called X region DE, because it's the clusters are in Germany. Then we have the local queues that match the other ones, and then we have this worker sets that match actual clusters. So basically, the clusters is what we just saw before. So that's the overview. And then for the demo, what I will do is you have here the master one. This is just monitoring the master one. This is monitoring the worker one on premises, and this is monitoring the remote one on the public cloud. So let's deploy some jobs. I will start with the on-premises one. So you can see it's created here in the master one, and then immediately it creates an instance of the job in the remote cluster. So actually, the main cluster is running nothing, just the metadata. The actual workload is running on the remote one. So that's pretty basic, but it's quite powerful. So you can see here I had my queues created, the local queues, which are the same. And then we have the multi-queue clusters, which is what I just showed you. So in this case, the job is actually running on this worker 3, which is on-premises cluster. So that's pretty cool. If we do for a remote one, an external job, whoops, yeah, this one. So it will be the same. It creates here an instance. And you have just the difference is that now I'm running in Germany, in some other cluster that I created. So it doesn't really matter. Like suddenly you can deploy Kubeflow, you can deploy whatever tool you want on your master cluster. It will just submit jobs locally. But then you can have, as an admin or a sysadmin, you can just attach clusters, remove clusters, and capacity as you go. And this works really well. Just to show you, I will just create a few of those. Like if I create more, you can see how fast it is. Like I'm creating more instances here. They are being created in this cluster, and they're up and running. And it's the same if I then delete them. Like if I try to delete 2 of these jobs, the ones I just created. This is super fast. Like they are gone and gone from the other one, and you can see that one even already completed. So you can get the feedback also in the main cluster. So this is pretty wild. Like it looks really simple, but the complexity of the thing, it's doing scheduling on a master cluster and distributing in multiple remote clusters. This is quite nice. Now the last bit of this demo that I will do is trying to submit the jobs with GPUs. So if I do that, you can see that it's created here. But you can see also that there's no instance running anywhere. And the reason for that is that we didn't configure, if you paid attention, we didn't configure any queue with GPUs. So you can see here that it's commented out and commented out. Now, I will do what's totally unreasonable, and my colleagues keep telling me to not do this, but I will do it, which is I'll do a live change in one of our production clusters. So I will just comment this out. And this is what we do daily. It's just managing this kind of thing. So I'll also commit to master. So we don't commit to master, but just for the purpose of the demo. They really don't like when I do this, but that's fine. So what I will do is I will commit this, and you will see the change appearing in Argo. So there will be a couple of changes that have to happen. So I have to reconfigure the master cluster. So you see it here, syncing. And you have to reconfigure also the remote clusters, because the queues also have to exist in the remote clusters. So this is what's happening. They are syncing. Took a couple of seconds. And now you can see that I have a job running with GPUs on my remote cluster in Germany. And it's been there for 6 seconds. So again, incredibly simple demo, but incredibly complex to actually achieve this on the tools. But we have the tools that make this really simple. So if you have, doesn't matter what kind of workload you have, if you're a single cluster, multi-cluster, you basically can do all of this. And it's incredibly important for machine learning. We just heard about GPUs. This is the main reason we need these features, actually. So that's my last demo. And they all worked, even without my lucky sweater. So. Now, what I'm really interested in hearing for the rest of the day here in the hallway is what can you do today that you would like to do with Kubernetes? And I think this is like the last 10 years have shown that this community is incredibly active, super creative, and has been covering for all the holes we needed them to cover. And it's been an amazing journey. So I'm really interested in listening to what all of you have to say. And thank you very much.